1955. The United States Navy unleashes a beast. The USS Forrestal. It was the world's first supercarrier. It was 1,067 feet long. It was 252 feet wide. It displaced 81,000 tons of American steel. It was the physical embodiment of a superpower that had just saved the world from tyranny. 2017, 62 years later. We launched the USS Gerald R. Ford. It is the most expensive warship in human history, $13 billion. It is powered by two A-1B nuclear reactors that can generate 3 times the electricity of its predecessors. It launches stealth fighters with electromagnetic rails instead of steam. But if you take a tape measure to the flight deck, you will find a number that defies logic. Width, 256 feet. In 6 decades of absolute global dominance, the American supercarrier has grown by exactly 4 feet. Length, virtually identical. Displacement, it hit 100,000 tons in the 1970s, and it stopped cold. Think about that. In that same time frame, we went from rotary phones to iPhones. We went from the Model T to the Tesla. We went from propellers to hypersonic missiles. But the pride of the U.S. Navy, the big stick of American diplomacy, has been frozen in time. Why? Why does a military doctrine built on overwhelming force, a culture that believes bigger is better, and a defense budget larger than the next 10 nations combined, accept this stagnation? Did we run out of steel? No. Did we run out of money? Never. Did we run out of ambition? Impossible. The answer is buried in the concrete, and it is hidden in the concrete and the mud. The U.S. Navy isn't choosing to keep the carriers at 100,000 tons. They are being held prisoner. They are trapped in what naval architects call the geometric cage. The enemies keeping our ships this size aren't the Chinese DF-21 missiles. They aren't Russian torpedoes. The real enemies are physics, geography, and industrial concrete. Today, here on Navy Decoded, we are going to tear apart the blueprints. If you want to understand the engineering that rules the waves, make sure to subscribe right now. We are going to look at the invisible walls that confine the most powerful weapon system on Earth. We will see why building a mega carrier isn't a sign of strength, it's a suicide note. And we will discover why 100,000 tons isn't a limit, it is the number of perfection. Let's tear apart the blueprints. To understand why we stopped, you have to understand how fast we used to run. The evolution of the U.S. carrier is a story of violent explosions, followed by long silences. 1922, the USS Langley, CV-1. Let's be honest, it was a joke. It was a coal ship, the USS Jupiter, with a wooden roof slapped on top. 11,500 tons, 15 knots. It barely had enough speed to generate wind for the biplanes to take off. It was an experiment. Then came the war. World War II. The shackles came off. We built the Essex class, 36,000 tons of war-winning aggression. These were the ships that broke the back of the Imperial Japanese Navy. They were mass-produced industrial miracles. But then, the sky changed. The jet age arrived. Propellers were out. Turbines were in. Jets were heavy. They were fast. They needed more runway. They needed more catapult power. The Navy responded with the Midway class, 64,000 tons. It was the first American ship too wide to fit through the Panama Canal. We broke the first geographic lock. We didn't care. We needed the size. And then, the quantum leap. 1955, the Forrestal. This is the moment the supercarrier was born. We jumped from 64,000 tons to 81,000 tons overnight. We widened the deck to 252 feet to accommodate the angled runway. This was the revolution. But look at the data. From the Forrestal in 1955 to the Nimitz in 1975, the length grew by 25 feet. From the Nimitz in 1975 to the Ford in 2017, the length grew by virtually 0. The hull form of the U.S. supercarrier has been essentially a photocopied design for 70 years. The Ford isn't a new shape. It's a Forrestal hull packed with 21st century dense technology. Why? Why not build a 150,000-ton ultra carrier? Why not a 200,000-ton floating continent? Imagine the power. 150 jets, unsinkable. It sounds like a dream. But if you try to build it, you run into the concrete womb. If you want to see the hard limit of American power, you don't go to the Pentagon. You go to Virginia. Newport News Shipbuilding. This is the only place on the Western Hemisphere capable of berthing a nuclear-powered aircraft carrier. Specifically, you go to Dry Dock 12. This is a massive, reinforced concrete pit. It is 2,172 feet long, and critically, it is 249 feet wide. Memorize that number, 249 feet. Now, let's look at the specs of the USS Gerald R. Ford. Flight deck width, 256 feet. Wait a minute. Do the math. The ship is wider than the hole it is built in, 7 feet wider. How do you fit a 256-foot object into a 249-foot box? You cheat physics. You use a technique called the cantilever. The hull of the ship, the part that sits in the water, is only 134 feet wide. It fits easily in the pit. But the flight deck? It flares out. It explodes outward like a mushroom cap. When the ship is being assembled, the edges of the flight deck literally hang over the concrete walls of the dry dock. It hangs over the service roads. It hangs over the heads of the workers walking on the pier. And here's where the cage slams shut. Running parallel to the dry dock is a monster called Big Blue. It is the largest gantry crane in the Western Hemisphere. It runs on rail tracks right next to the pit. The gap between the edge of the Ford's flight deck and the leg of the Big Blue crane is measured in inches, not feet, inches. If the Navy wanted to build a carrier that was 150,000 tons, let's say with a 300-foot beam, it wouldn't fit. The flight deck would smash into the crane. To build a bigger ship, Huntington Ingalls Industries would have to demolish Dry Dock 12. They would have to tear up the rail lines. They would have to rebuild the entire industrial infrastructure of Newport News. The cost? Billions. And that's billions of dollars spent before you even weld the first piece of steel. The CVX studies in the 90s looked at this. They realized that the infrastructure cost would kill the program before it began. So, the USS Ford is the exact size of the tool used to make it. It is a cast of its own mold. We aren't building the ship we want. We are building the ship that fits. But let's say we did it. Let's say we spent the billions. We built a megadock. We built a 200,000-ton monster. Congratulations. You have just built the world's largest prisoner. Because now, it has nowhere to go. Aircraft carriers are tools of freedom. And freedom requires movement. But the ocean is not as free as you think. For a ship with a 40-foot draft and the height of a 24-story building, the world is a maze of choke points. The most dangerous one is in Egypt, the Suez Canal. This is the jugular vein of global strategy. It connects the Mediterranean to the Persian Gulf. If you can't use Suez, you have to sail around Africa. That adds weeks to response time. It burns millions in logistics. And worse, it eats away at the precious, finite lifespan of the nuclear reactor core. Here is the rulebook of the Suez Canal Authority. Maximum allowable beam, 254 feet. Now, look at the USS Ford. While its hull fits the channel, its massive flight deck spreads out to 256 feet. Technically, the hull fits, but the wingspan is a hazard. The ship is a special operation risk. The flight deck literally hangs over the canal banks. A sudden gust of desert wind acting on that massive surface area can push the ship into the sand. The pilots don't just steer, they fight the aerodynamics to keep the ship from drifting. But the trap isn't just the width, it's the ceiling. Look up. Spanning the canal is the Al Salam Bridge. The clearance height is exactly 230 feet. On older ships, the Navy used folding masts to duck under bridges, but the Ford is different. It carries the new dual-band radar, the most sensitive eyes in the fleet. These massive radar panels need a solid, immovable foundation. They cannot shake, and they certainly cannot fold. So the architects faced a brutal constraint. They had to design a 100,000-ton fortress to fit inside a box defined by a civilian bridge. The result is the integrated mast, a fixed composite monolith. It doesn't bow, it doesn't fold. It is sculpted to clear the Al Salam Bridge, but only just. It is a game of inches. Imagine piloting a 24-story building under a concrete beam at 10 knots. If the calculation is wrong, or if the tide is unexpectedly high, you don't just lose an antenna, you smash the ship's brain. The Ford fits, but it fits with the terrifying precision of a bullet in a chamber. And the cage gets tighter when you try to come home. Let's talk about mud. At Naval Station Norfolk, the home of the Atlantic Fleet, the channels are maintained at 50 feet deep. But nature hates depth. Silt and sand fill those channels at a rate of 2 feet per year. The Army Corps of Engineers is on a permanent dredging treadmill. They are digging 24/7 just to keep the channel open. If we built a 150,000-ton ultra carrier, it would ride much lower in the water. Its draft would exceed 45 feet. That destroys the safety margin. A bigger ship would literally be dragging its belly through the mud. It couldn't enter Norfolk. It couldn't enter Yokosuka, Japan. It would be forced to anchor miles offshore, relying on smaller boats for resupply. It would be a homeless king. The Earth itself has set the limit. 100,000 tons fits. Anything more gets stuck. But the critics still argue, who cares about the canal? Who cares about the dock? We need more firepower. We need 120 jets, not 75. This is the Walmart mentality. Buying in bulk means better value. In naval warfare, this is dead wrong. In the 1990s, the Navy and Rand Corporation ran the numbers. They looked at designs for large carriers carrying 100-plus aircraft. They found something shocking: the law of diminishing returns. A flight deck is a finite ecosystem. It is about 4.5 acres. If you jam 120 planes onto that deck, you don't get more airstrikes. You get a parking lot. You create gridlock. Aircraft have to be moved just to let other aircraft taxi. The bomb farm gets blocked. The catapults can't cycle fast enough. The metric that matters isn't hangar capacity, it is SGR, sortie generation rate. How many bombs can you put on target in 24 hours? The Nimitz class can sustain 120 sorties a day. The Ford class targets 160. How did they get that 33% increase without making the ship bigger? They didn't look at bigger ships, they looked at NASCAR. They analyzed the pit stop. On the old Nimitz, the bomb farm was in the wrong place. To load a GBU-12 on an F-18, the aviation ordnanceman had to push bomb carts across the active taxiways. Imagine trying to refuel a race car while crossing the track during the race. It's madness. On the Ford, they moved the island back 140 feet. This opened up a massive pit row in front of the superstructure. They installed advanced weapons elevators that use magnetic motors to shoot bombs straight from the magazine to the flight deck, right next to the jets. No crossing traffic, no waiting. Land, refuel, reload, launch. It is a closed loop of violence. The Ford generates more combat power than a hypothetical 150,000-ton monster because it is faster, not bigger. It is density over volume, efficiency over excess. But efficiency is only half the story. There is a seductive whisper that haunts the Pentagon. Why not go bigger? Why not build a 150,000-ton Titan? It sounds like the ultimate weapon. But when the Navy finally ran the numbers, they didn't see a fortress. They saw a trap. Back in the 1990s, the Navy asked a dangerous question. With the Cold War over, the admirals looked at the aging Nimitz class and asked, why stop? Why not smash the 100,000-ton cage? Why not build a 150,000-ton Leviathan that carries 120 jets and rules the ocean forever? They launched the CVX program to design this dream, but as soon as they looked at the blueprints, the dream turned into a nightmare. They realized that building a mega carrier wasn't an engineering challenge, it was a suicide note. The first catastrophe is economic, the prototype trap. The genius of the Ford class is that it rests on a legacy. We have 50 years of hard data on exactly how a 100,000-ton hull behaves in the ocean. We know the stress points, we know the steel. If you build a 150,000-ton ultra carrier, you throw that library of knowledge into the trash. The CVX report warned that a new hull form would reset the industrial learning curve. This causes the cost per ton to skyrocket. You wouldn't be building a standardized warship, you would be building a massive, unproven science experiment. And in naval shipbuilding, unproven experiments don't just burn money, they burn decades. But let's assume Congress wrote the blank check. Let's say we paid the price and launched this beast. Now, you face a darker enemy, hydrodynamics. Water is 800 times denser than air. As the ship gets wider, the drag doesn't just add up, it multiplies. To generate enough wind over deck to launch heavy bombers, this massive hull would need to sprint at 30 knots. But the physics don't add up. 2 nuclear reactors wouldn't be enough. You would need 3, maybe 4. This creates a death spiral. More reactors mean more weight. More weight means more drag. More drag means you need even more power. The result is a toothless tiger, a ship too fat to run, unable to launch its own aircraft on a calm day. And ultimately, even if you could